this year. We didn't have an engineer. That didn't seem hard. When Bill and I told him, yeah, we were like,
butt heads all the time.
Yeah.
The slides are definitely on the, the TV screen there on the projector screen.
In the back screen.
In the back screen.
Yeah, really.
Just things streaming over, looking at people, does it see? That's fine.
I insisted on.
So he believed it.
It doesn't happen that often. Deans typically they about themselves as administrators. They like to see.
Okay, my son's 10. He's right on the cover. Okay, thanks, John.
So I insisted on teaching.
We're still learning the lesson.
Teaching first year.
Should we get on?
You have to know what language students you have. I also had a graduate class as well with not a PhD. Okay. That's you.
Good? Yep. I'm just going to sit in and grab a chair.
Yes. I'm very excited.
I have to see.
So hello everyone, I'd like to welcome you today. I'm Alicia Goddard. I am a master's degree candidate here at Brock in environmental sustainability. Today we have a real treat. I'm going to introduce you to Dr. Koziński, who is a well-known internationally as a higher education leader, researcher, and entrepreneurial working in the U.S., Europe, and here in Canada. He's recognized globally as an expert in sustainability, energy systems, technology, and science. He's the author of over 400 papers, books, and conference proceedings. Among his many accomplishments, he's been the Dean of the College of Engineering at the University of Saskatchewan, the founding Dean at the Lausanne School of Engineering at York University in Toronto, which included establishing a Renaissance engineering program. Most recently, he served as the founding president and professor of Britain's Hereford University of Technology and Engineering, which is on the cutting edge of both education and engineering concepts. He leads multidisciplinary research teams and programs linking energy, environment, public health, and security issues. His research has focused on projects involving security of buildings vulnerable to bioagents, improvements to nuclear reactors, environmental impact of energy technology, greenhouse gas mitigation, and the fabrication of nanomaterials. He's even been involved in the exploration of Mars. His investigations have been applied to handle everything from biomass conversion to environmentally neutral biofuel production and mitigation of nuclear waste. He is currently serving here at Brock University as the special advisor to the president and at Waterloo Institute of Technology as professor. Today he's going to talk to us about the symbiosis, a new type of symbiosis, a cooperative, mutually beneficial relationship between energy and the human environment. Please join me in giving a warm welcome to Dr. Koziński.
So you're very, very kind. Most of these things were written by my public relations people, so they are highly exaggerated. Because things look really good on paper. How I work anyway, I never look back. So indeed, I had some administrative positions and research and so on. What's really important is to look into the future. So for me, the most important thing that I will be doing for some time, I hope, is to be here on campus, try to make life easier for students, faculty, and also give an honest advice to the president and some other colleagues in the administration. Now, indeed, I will be talking about symbiosis, predominantly about energy and environment. but it also will be linked with symbiosis between people. And that's whatever I do as a researcher, and I think about myself predominantly as a researcher or a teacher and so on, then it's absolutely fundamental to put a person at the center of everything what you do. And at the end, I will comment on a project that we are developing here at Brock, where we're putting our students, well, future students, at the very center of our activities. But before we get there, what I wanted to do is to share with you some of my experiences, because there are moments in your lives, and I'm sure some of you have had it already, some of you will experience it, that there is always a sort of a breakthrough, that you start thinking differently, that you start seeing others differently, that you're looking at yourself in a different way as well, and most importantly, that you're going to appreciate others in a way that is definitely different than what you were thinking about than before. For me, it was an opportunity to go to space. So let me start with my experiences there. I went on something, it's called a Parabolic Flight. So what it is it was in France. It was organized by the European Space Agency and the Canadian Space Agency. I was the only scientist from Canada at that time involved. We developed an idea what to do in order to go to Mars, land, go around, collect samples, and come back onto the Earth. It's impossible to do it, by the way, with the current technology, because you would need to carry out so much fuel that you wouldn't have been able to even have a takeoff from the Earth. So we found out about, we proposed something interesting with a colleague of mine from France and another one from Japan. And I'll tell you all about it later on. But what it is, the parabolic flight is very interesting, because what you do is you go up at the angle that you see. You seldom see an angle like that. So you are at around 4 to 6 gravity forces. You can't move your leg. You can't move your hand. Blinking an eye is very difficult. Everything is so heavy. And then when you reach the altitude, and in our case it was just shy of 40 kilometers. So space technically starts at 40 kilometers, 40, 60, and then later on. But anyway, everything is pitch black about you. So you reach the altitude, and they switch engines off. So if you have an airplane and the engines are switched off, well, you're just falling down. And when you're falling down, the weight of the aircraft is much heavier than your weight of your boat. So you are weightless. Actually, you're floating. It's all formed inside, actually, everywhere, because you're hitting the walls and so on. And so you're going down to approximately maybe 5 kilometers. And depending on the trajectory, it is somewhere between maybe 25 to 60 seconds, 70 seconds. And then when you're there, then again, the engines are put on and you're going up. And then, so we did it 28 times. But anyway, so it took altogether almost 7 hours. It's 28 times because if you're doing a scientific experiment, as you well know, you have to have some repeatability. You have to have some data. And in our case, some of the parabols we simply didn't do much because we were just enjoying it, floating in the air. So look, when you're going up and down, your stomach is trying to jump out of this way, or your mouth, or the other way. And it is, some people have difficulties to to sustain it. So it's also called, those parabolic flights are also called a vomit comet. And there is some reality to it as well. So essentially that's what we had done. And then when you're up there, I went to the cockpit, and then you see the curvature of the Earth. And you see how small, really, really small we are. And it's incredible how small we are. And then this is where you start thinking differently about yourself, about what you do, about how you behave, about others as well. And up until then, by the way, it was 2002, 2004, and up until then, I thought about myself predominantly as a researcher. That's what I would do. I have to say, although it is televised, but I would be dishonest if I didn't say so. When I was a prof at McGill, mostly focused on research, I considered undergraduate teaching as a nuisance. All right? I'm sorry about it, but I have to be on the why so, because you want to do research and so on. And what came to me when I was up there is actually the most important thing of what we do in academia is to make certain that we are able to interact with young people, with undergraduate students and graduate students. I'm using interact rather than just educate, because education is one element of it. You can educate via research, you can educate via the personal interactions. So that's where I came to the conclusion that what I have to do, together with some of my friends, we have to find a way to develop new ways of thinking about education, but also new ways of thinking about research, so we can educate mostly graduate students by research. And I will comment on some of those outcomes of those ideas later on at the end of my talk. But before we get there, what I really wanted to do is to share with you a few things, what we had done from the research perspective, especially linking different forms of energy and environment. I know some of the background that I'm going to share with you. I'm certain you know because of your because of the classes that you've taken. But I wanted to put it in a certain perspective. So let me share with you why is it that we're dealing with it, and well, why so? Because energy. When you generate energy, you're always going to generate pollution, a variety of pollutants. And it could be something like polycyclic aromatic hydrocarbons. These are cancerogenic and mutagenic substances. And it could be as simple a substance as CO2 or other greenhouse gases. So those are the greenhouse, this is distribution of emissions of greenhouse gases predominantly linked with the generation of energy. So you can see there's a very high correlation between the top economies in the world. So the US is thus far #1 economy in the world. China is #2 because of the difference in technology that they are using. And there is a lower emission, but it's staggering. Actually, we are contributing quite a lot. By the way, 1.5%. It is quite a lot. Well, it is at least 0.7, 0.8% more than we should have. So the greenhouse gases are generated predominantly by the everything that is related to producing energy. So we produce energy to live. We have power plants. Actually, on this campus, we do have a power plant. It used to burn coal, I believe, some time ago, but it is natural gas now. So a lot of people, they say, well, natural gas is clean. There's nothing clean about it. It's cleaner than coal, but we may want to find different ways to generate energy. Or when you use your vehicle, when you drive, you also, transportation is one of the sources of energy, of pollution as well. So if we look at the contributions, the trends of CO2 emissions, and over some period of time, there are a few interesting observations. So to be honest, in general, it's a relatively positive trend, because when you look at countries like the United Arab Emirates or UK, the trend is, in general, that it's going down, or US. Poland, I should mention that I was born and raised in Poland, so I have always a sweet spot for my country. But there are just a few aberrations or different trends. It's China, so it is going up, and South Korea. So essentially, it tells you those are the countries that are growing their economies. It's very important for us to consider the next generation of countries that will be growing their economies, such as India. Do we have India here? Oh, perhaps not. Such as India or countries in Africa. Is absolutely critical that we're going to provide proper assistance with regards to next generation of technologies in order to reduce or eliminate the trends that we see in South Africa and China. Canada is doing all right. The certain trend is there, although if you just average everything out, it is more or less stable. So if we have, those are the main sources. The main sources of CO2 that are, of course, fossil fuels. So if we look at the distribution of the contribution of different kinds of fuels, gases, and liquids, and solids, you will see that the solids are still contributing the most. So do you know, if you could give me an example of what would be a solid fossil fuel?
Coal.
Exactly. It would be coal. How about liquid?
Gasoline.
Gasoline, yes. Yes. In the UK, they would say petrol. Yes, so it's a gasoline. And gas, of course, it would be predominantly natural gas. So, by the way, so it is true that the contributions from gas is lower than from the other. That is absolutely unacceptable. And can you imagine between 1940 and 2000, it's 5 times higher the emission. It's absolutely staggering. So we need to see what would be the potential sources of energy in order to reduce that trend. We have to have energy to live, there's no question about it, but we have to find different sources of energy. So one source, of course, which is very controversial, it is nuclear. Nuclear energy does not contribute to greenhouse gas emissions, but until we find an opportunity to deal with the residues, radioactive waste, then it will be very, very difficult for the society to accept nuclear as a viable source. In Canada, actually, especially in Ontario, we have a much higher proportion of electricity generated by nuclear. And I worked on several strategic projects related to nuclear industry. And at some point, I became disillusioned because we had terrific ideas, by the way, how to develop a next generation of nuclear reactors, predominantly reactors that are not using uranium but thorium. So you don't generate. You don't need to have that much plutonium. You don't generate a high radioactivity, and the waste is not radioactive whatsoever. So it was quite an interesting concept. But then we were told that there is an opportunity potentially to test it out in about 40 years from now, and then we'll see what would be next. And then I realized how conservative is this industry. So we decided to focus on some other things. One other thing, well, the two sources of energy that we liked for different reasons. One was biomass. So biomass, essentially, those are residues, and I really focus on this as residues from forestry, residues from wineries, rather than dedicated crops. There are some in the US and in Canada. We do use specific crops, but then there is a moral issue, because if you dedicate land to grow crops, then of course you don't use that land to generate other things that people need to live. So our focus is exclusively on residues that are generated by a variety of industries, mostly agricultural industry, forestry. So in Canada we have quite a lot of that, although US is much more substantive from that perspective. So biomass is one of the sources of energy. The other source, what do you think, what are the other sources actually? Before I click, then what do you think? Well, look, some renewables, wind could be as well. But from the practical perspective, the other potential source, and it is considered as fuel of the future, is hydrogen. Now, I put a question mark there because we were already saying so about 15 years ago that hydrogen is going to be a fuel of the future. Now, the problem, of course, so the good thing about hydrogen is it's in abundance in the universe. Well, hydrogen is the main component of water as well. So if we are able to find a way to split water, then we would be able to create hydrogen. So water is H2O. If you split hydrogen and you have oxygen, then you will be able to use a portion of hydrogen to generate energy and another one to put it back with oxygen. So you would have water in perpetuity and then generate energy. But hydrogen, we wrote a paper about it. But when I say we, I exaggerate a little bit because it is, and thank you so much for saying that we've published around 400 papers and so on. The majority of those papers were generated by graduate students like you. I don't know what is the culture of application in your field, but in engineering, typically what we do is we have quite a large group, research groups, and when I was coordinating such a group, it was truly eclectic. So we had people from medicine, from physics, from chemistry, from psychology, engineering, of course, and I really wanted to have that group so our graduate students were able to learn about, were able to look at the same problem from a variety of perspectives. So in our field, always the graduate student or a postdoc would be first author, and then others who contributed to it would be the next authors, and typically the most senior researcher would be the last. As you can see, senior researcher means that you are relatively old, so I'm not there as yet. Yeah. But anyway, so hydrogen, you have a variety of ways to do it. The problem with hydrogen is that it is very dangerous. If we had some liquid hydrogen here and having oxygen from the air, it would explode. I think you may remember or know there was a Challenger which was a disaster back in 1976, and the problem with so it was a shuttle that would go to space and explore many things and then come back onto the Earth. So the problem was that there was a leak. Actually, there was a gasket, just a small gasket that broke off, and liquid hydrogen. There were two tanks. One was liquid hydrogen, the other one was liquid oxygen, in order to generate energy. So it was controlled and it was perfectly all right. But once it broke off, then they couldn't control it, and it was a huge explosion. So if we had a bit of it here, it would create a lot of explosion. So safety is the main issue. The other, of course, is the cost of generating hydrogen. So I will tell you about what we came up with, and it is, well, from our perspective, it is a cool idea. So we'll see what you think about it. But before we do so, let's take a look at the hydrogen production. So the US is in the league of its own, really. Well, why so? Because they need hydrogen for a variety of military applications. So it's actually here, it's not driven by sustainability of the environment and so on. It's driven by different purposes, and it is also being used for different purposes. Now, in our case, we are doing quite all right. Well, you can see that there's just a little bit of a drop. And why so? Because some years ago, I think maybe around 17 years ago or so, Canada believed that we will be able to develop fuel cells. So fuel cells, they work in a way that you have to feed it with hydrogen, but they are very clean, and then you can use it for transportation. The federal government invested a lot in these technologies, and fuel cells never picked up. So that's why, in our case, it's just a little bit of a drop. Now, so what we decided to do, when we, meaning at that time, we had a truly eclectic group of researchers, as I mentioned, a medical doctor and a lawyer and an engineer, a scientist, biologist, physicist, and so on. We would get together every week at McGill at the faculty club. Yes, and I was sorry to hear that we don't have faculty club on our campus, because it was such a stimulating environment to spend 2 hours over a glass of wine, and we would always invite our students. Sometimes we would play snooker and so on, but it was all about having a discussion about our research. So to the point that at some point well, initially, by the way, because it was a truly multidisciplinary group, we would argue a lot, and because the nomenclature that my colleagues in in medicine would use would be, we would talk about the same things but slightly different words. So we would it took us at least half a year to find a consensus about the terminology. What does it mean to you when I say something? Once we did that, it was seamless. It was absolutely wonderful. To the point, I will digress a little bit. So to the point that what we would do, we would have in engineering, every Friday we would have graduate seminars. Sometimes it was relatively dry, depending on the subject, the speaker, and so on. So we wanted to spike it up. So one day I invited a friend of mine. He was a poet. He was a so-so poet, but he knew about poetry a lot. And then another friend of mine, he played flute. Actually, he was one of those. They received an Oscar for creating music for a documentary. So David. David would play flute, and then my friend Matthew would recite poetry. And we selected poetry from the countries, all countries that our graduate students came from. And it was absolutely incredible. I remember we had at that time quite a few graduate students from Iran. And he selected a poem by Rumi. It's a very well-known poet. Well, his poetry was forbidden in that country. I take a look at it, and I still remember it was many poems about love, okay, which was great. But it was also about oceans and blue water and so on. So you could close your eyes and you could see it. I mean, it was incredible. And the first time I saw my graduate students from Iran crying, male students. I mean, it was so powerful for them. And so it was one of the most successful seminars. They still comment about it. Sometimes I get Instagram, so they are still saying a few things about it. And then we did another one. I invited my friends from opera, so we had a baritone, and then we had a soprano, and so on. They came dressed up, and they sang the songs that are very, very well known. It was absolutely terrific. Can you imagine? Engineering students, and then they are exposed to it. It's very important to do so. It's absolutely critical to make certain that students have an opportunity to enjoy not only the fruits of their research, that they are able to enjoy the fruits of what humanity have generated. Look, so what after those faculty club meetings, after a few glasses of wine, after some poetry, and after listening to baritone and soprano and so on, we came up with an interesting idea to use water to generate hydrogen, but to stimulate this by using those residues from forestry. So what we decided to do is use supercritical water. Now, please forget. So, by the way, supercritical water, just for those who want to know what it is, it's just water at a temperature above 374 degrees C and above 218 atmospheres. So it's not that high a temperature, but very high pressure. This is a PT diagram actually serves, and I know that you may not be that much interested in it, but essentially above critical point, there's steam does not exist, liquid water does not, isotope, it's a completely different state. So water in supercritical state is the best solvent there is. So if this is a container with supercritical water and we inserted any organic material like pieces of your paper or a human hair or so, or something really big, as long as it is organic, it would dissolve everything, decompose everything to individual atoms. So you would have hydrogen up there and then nitrogen down here and so on. And then what you can do is, so you would have a relatively, could be a relatively nasty substance. So it could be a residue from hospitals, for example. So some residues of parts of human body or so. That it would decompose everything to individual atoms, and then you can take carbon and you can take nitrogen and you have a carbon nitrate or whatever. So it's a very powerful technique because it's a low temperature, then no pollutants are generated. So no nitrogen oxides, no sulfur oxides. pH stands for the polycyclic aromatic hydrocarbons. Those are organic substances, mutagenic and cancerogenic. The key product is any combination of hydrogen, CO, CO2, and of course what we want to do is minimize this and maximize that. All right. The problem, of course, is that studying these the processes in supercritical state is extremely difficult, very difficult, and especially doing it in situ, which is studying as things occur, is very, very difficult. So there are many different applications for it. One of the first applications, it was you see, when astronauts go to the International Space Station, or even if they are on a multi-hour flight, they are human beings. They have to go to a bathroom from time to time. Well, maybe next time I tell you what our current Governor General, the Governor General, Julie Payette, she's an astronaut. We had dinner sometime ago together, and she explained how it is when astronauts go to bathroom. It's a very peculiar process, actually. So anyway, but there are some residues that were generated by people, and NASA used supercritical water to decompose because you have to deal with those things in the space. Extraction industry is good. So what we were also doing is we used supercritical water to help with destruction of chemical weapons. You may remember that a few years ago, it was still under Obama administration. There was an agreement that Syria is going to get rid of chemical weapons and so on. And one of the main methods that were used to destroy it, because you wouldn't want to stockpile, you want to destroy it. It was actually supercritical water would, if you have a substance, it would decompose chemical substances to individual atoms. Very powerful, very difficult to study. So what we found out that in order to have information what's happening during the process and how to conduct process in a way that it is safe, we used a diamond anvil cell. This is what physicists typically would do to study processes what's happening at the core of the Earth. So the core of the Earth, it's a high temperature, very high pressure. The size of it is like having two hockey pucks together. I remember I had a lecture in Abu Dhabi some time ago, and I wanted to explained to them how it looks like, and how the diamond tunnel looks like, and I mentioned about hockey parks and so on. They didn't have a clue whatsoever. Yeah, so it was really fun. But anyway, so it's around, well, let's say here it's maybe in diameter 15 centimeters and another 10, and right in the middle of it there is this two diamonds, and in between the diamonds there is a reaction chamber, which is what we study what's happening. The size of it is around 500 micron, half a millimeter, in length and maybe in diameter, and around 200 micron in depth. So this is how it looks like. I have to show it to you because otherwise it may be different. So you have one diamond. There is in between. It's a gasket. This is where the sample is going to go together with some water to create supercritical water or hydrogen peroxide, so it's a little bit more oxygen. Then you have another diamond squeezing the sample that is in between. Everything is heated up because don't forget the supercritical water, you have to bring it up to 374 degrees C, and at the same time temperature to 200, pressure to 218. So you have to heat it up, and then you have to cover it in order to protect. Now, I remember one of my PhD students that he forgot to attach one screw. There are 12 screws around that diamond anvil. And we were doing those experiments, and with hydrogen, and there was, of course, there is hydrogen and there is some oxygen, and it exploded. Now, so the top of the diamond anvil, it was in the lab bigger than this a bit. It went through the wall, made a hole in it, went through the corridor and made a hole in the next wall. So it was very, very serious. Now, perhaps it added to it, it was back at McGill when I was there, it added to it because at that time I was the chair of the University Lab Safety Committee. Needless to say, it was embarrassing. We worked it out, but it tells you how this is. Now, so then what you do in my field, we always have to measure things. Measurement is fundamental to everything. So we had some thermocouples. So those are the things that measure temperature that we use, and we wanted to see what's happening. And since you have diamonds, then everything is transparent. So we would link it with a microscope, and then we would see what's happening. And then sometimes we would put it under the Raman microscope. That's an interesting microscope. You can, in addition to seeing, you can measure what's happening. That is really cool instrument, I have to say. When we created this assembly, it was the only one in Canada at that time. Now, so we would have sample. Now, and then what we needed to do is measure also pressure. So we would have a bit of a ruby. The ruby. Well, why is it? Because ruby would emit light at different wavelengths proportionally to the pressure that there is. So we would use a laser to ignite or stimulate ignition of the biomass, and then what we would do is we would measure the change in pressure that was indicated by ruby. So that's all of it. By the way, this is relatively straightforward. I'm just making a little bit more around it than it is. It's not easy to control, but at the end, in research, as you know, the key element is the idea. If you have an idea, you can always find a way to make it happen. So this is how it looked like. The diamond anvil, plenty of wires to measure, and then we put it under the microscope, and then we would study what's happening. Now, And typically I would go into more details about chemistry behind it and so on, but I will not. Because at the end, what really matters is what is the outcome. So what we have done, and there's one conclusion that it will be very useful. So we developed, and this is what we typically would do in engineering or science. Well, we would study the profile, so it would be what's happening with different compounds over a period of time. So something like, so if we would use very nicely substances, benzoylpyrene, one of the most cancerogenic substances. So we would the purpose would be to destroy it. So we would destroy it, and then we would see, well, if this is going down, then something like phenanthrene and acetylene and so on. The key was that we were able to control the process the way that the only product was hydrogen. It's a powerful statement, because what we would do is we would use the residue biomass coming from agricultural operations residue, and we would generate in a safe way, except that experiment that my student had done. But in principle, in a safe way, we would generate clean, fantastic fuel, and we were able to generate it on demand. It's another important thing, because when you generate too much of hydrogen, you have to store it somehow. So this is what we would do, and then we would go to something more elaborate process, and I will just go very quickly through it. So in science and engineering, the important thing is to understand why things are happening, and what is it that happens from the beginning to the end. So we studied the evolution pattern. So then we would know that if you have this kind of substances, they would evolve, and we've observed something interesting, that there was certain products that always existed when we were dealing with this benzoylpyrene. And then what we would do is we would look at polystyrene. So polystyrene is the main substance in plastic material. So your cup is predominantly made of polystyrene. So what we would do is we would study what is happening, and we observe that at some point everything goes to one place, which is terrific. And then there will be the final product. What it tells you is, from the practical perspective, that you can use you can have a different kind of materials. You can have a different kind of geometry. You can different kind of reactors, because as long as you know how to decompose just a few substances, then you will be able to be all right. So that's what we had done. Now, it stimulated those. It was a product of a very multidisciplinary approach to it, because at the same time, I'm not commenting on it, we were testing what is the level of cancerogenicity of some of those substances, or how they influence human body. What would happen if you inhaled? It would just go to your lungs or kidney, how it would mutate your cells and so on. So I'm setting it on the side. But what was the important thing for us, it was to understand that we have to find a new way to educate our own students about the necessity of working together and doing it in a sustainable way. So if you look at the academia right now, or higher education, indeed there are substantial forces that are influencing what we're doing. Well, one of the most important ones is your own expectations. Because when you come to the university and you invest your time, money as well, but I think time is much more important. I mean, you could do different things in your life, but you decided that that's what you want to do in your life. So your expectations are becoming higher and higher. Actually, what the young people should do is demand even more from their universities. You're not demanding strongly enough as yet. It's very important. Well, maybe I'm not saying you specifically, because when I look at the rankings, and I don't believe that much in ranking because I know how it works. I was an administrator, and I know that the same numbers you can present in many different ways. One ranking that really is important, and that is the one that defines the character of the institution, is the student satisfaction survey, because it comes from you. And Brock is number 3 in Canada overall. That is fantastic, actually, and it was just released. And it's number 1, I believe, in offering mental health assistance. It is number 3 in offering academic advising and so on. So if you're not satisfied that much, it tells you how other people are, other students from other institutions are what kind of services they are getting. But you have to remember that universities exist because of you and for you. I mean, people like Professor Planner and myself, we are here because of you. It's the critical driving force. Well, there are some other driving forces like technology, and in our case here in Ontario, also governmental policy, because there are some government insists on having strategic mandate agreements with universities, and also diversifying universities and so on. But indeed, there is a need for educating young people at universities in a different way. So you see, what brought me here, it was the aspiration, here meaning Brock, aspiration and ambition of this university to create something new, bold, and different, and a new program would be focused on engineering, but linked with everything else that the university is doing. So it's terrific. I like to build things. I remember when we created the Lasson School of Engineering at York, came up with the idea of Renaissance engineering. In Renaissance, that's what people would do. They would sit around the table and think about things and talk about things. And I remember creating I called it a Camelot. So Camelot, what we had a truly open table, and it didn't really matter if you are a dean or you are a graduate student. So we were driven exclusively by ideas, and it was a fantastic feeling. But you have to be also practical a little bit about it, because once you have those ideas, then you have to implement it. So we had a smaller body, and we called the Full Monty. And the younger people, you may not. So Full Monty. Well, essentially, what it was not what you think, actually, because it was the body was to strip everything to bare bone, and then make decisions and implement them very, very quickly. Yeah, so that's what we meant. Nothing different. So that's what I looked at it, and Brock indeed is one of the very, very few institutions without engineering, and a different kind of engineering. So I asked myself a question, and I asked this question of many other colleagues as well. If we are to create an engineering, what would it look like? What is the really, really great engineering program of the future? And then we scrutinized everything to 4 meaningful questions that we saw. So what we need to do, whatever we do, we would need to try to answer the 4 questions. So one is about the smart living or smart cities. And I'm sure in your program, and I know that colleagues from the center, they are involved in a lot of these projects, how we can secure everything. So that includes, for example, cybersecurity or security of social networks and so on. Now, how we can benefit from living organisms to reassemble them in order to have the kind of devices or sensors that are going to help us, and how we can benefit from not just autonomous vehicles, because a vehicle is a car, is an example of the way of thinking, how we would have about the future of a variety of engineering systems. Now, everything, all these things, they have to be placed on a very, very strong foundation of sustainability. That's why what I was really, really happy to see that one of the strongest areas of activity at Brock is around your center. It was fantastic, and it was, I think, one of my first conversations that I had outside of colleagues in the administration. It was with Professor Plummer, and it was revealing. I loved it, actually. Now, so what we decided to do is to, and by the way, what I will be showing to you, a lot of colleagues from the university haven't seen it as yet. So, those are ideas. I hope that we're going to land somewhere, and some of those ideas are a bit controversial, perhaps more than a bit. But nevertheless, I want to share it with you because I'm also interested in your opinion. And I understand that we may have a limited time, so if you are unable to offer your opinion now, then please send me a note. I'll be happy to share a tea or coffee, and we can discuss it later on. So, if you're going to create a new program, you have to be bold and you have to be different. You have to be careful, however, because you want to be different, but you don't want to be odd. Because then people are not going to take you seriously. So it's a fine border, and that's why I believe the message that I want to take to the community is predominantly to talk to students, because I want to make certain that it resonates with you. So, I think that lectures are passé. I don't think that you're going to learn a lot in the setting that we have here. You see, this is, by the way, it's a painting. It's a Henry of Germany speaking in the 14th century at Bologna University, one of the oldest universities in the world. To be honest, in engineering, I know how it is in your field, but in our field, in engineering, this is mostly how it looks like. There's a prof sitting in front of a class and then teaching. And I'm sure there are many very good professors, so indeed you can learn something. I'm not saying that you're not going to learn, but there are quite a few suboptimal teachers as well. And I'm sure you've experienced those. I did too. So this is it's something that we wouldn't want to have. And by the way, if you look at it, it's like a real classroom. You have some people that are really enthusiastic about it. There are some that are not. Actually, if you look at it, more are not than they are. So, no lectures, but you have to replace it with something meaningful. So what we are trying to do here, we are developing the concept of an engineering studio, a Brock type of an engineering studio. and I will explain to you later on logistics, but what we want to do is to base the program that is exclusively focused on dealing with real projects that would be coming from employers. By the way, when I say employers, it doesn't mean industry only. It means also community centers and financial institutions. It means educational institutions of variety. And we came to the conclusion that the best way is the smallest group that will be really performing well is 5. So this is the home of a group of 5 students that would be working on specific projects coming from employers, and these 5 students would be provided assistance or mentorship from an eclectic group of professors. So it would be an engineer, would be a scientist, would be an economist, would be a medical doctor, a lawyer, an entrepreneur, a psychologist, and so on. So they would be spending 3.5 weeks and working in sprints. I will explain in a moment what it is. So, but some of the projects will be much more complex. So the largest group ever would be 25, and so this is more or less how the studio would look like. By the way, this is real. It's I mean, we don't have it as yet. But you will see, we're going to try to test it out next year. So if you're still around, it would be terrific having you to test it out and let us know. You will be a pioneer, and I bet you, we're going to learn much more from you than you will from us. So this is the larger group. And if we have some time later on, then I can explain you what we mean by those sprints and how we're going to work in the logistics department. The other controversial thing, well, controversial perhaps from the professorial perspective, not necessarily from student perspective, is there's no reason to have exams. Exams are, in my opinion, unfair. You see, because you work during the semester, and then at the end of it, and by the way, I'm not saying that you personally, but at least in my field, the students work for the semester, and then at the end, on a Friday evening, they have a 4-hour exam, and if you don't feel good about it, or if you heard something that is not good at home, or if you broke up with your girlfriend, boyfriend, and partner, and so on, then it's absolutely unfair to assess performance throughout the entire semester of a student based on the exam. And I realize that exams are the proportion of your grade. But the idea, actually, would be to assess students based on their portfolio of achievement. So all those projects that they would work on, they would generate some, like most of the time, they would generate something tangible. So they would make something, design something, manufacture something. There will be some of those projects on purpose that you have to fail. Actually, because you will see, you're going to learn much more from failure than from success. So that's what we're thinking about. But we have to find a way to assess you as an individual, not only you as a member of the team. So this is what we have in mind, actually. We're thinking about, rather than having in engineering mechanical, civil, electrical, and so on, this is not how engineering works. You work around particular areas. So we were thinking about 4 areas that we're going to focus our program around. So feeding the world, which is agri-food, agri-tech, water, shaping the future. It's manufacturing, robotics, augmented reality, living in harmony, those are the things related also to policies, for example. And a healthy planet is related, you may need to link some of the work that is being done in our the Faculty of Health Science, for example. So then, those are the different areas of focus. Then we would need to have strong engineering concepts. So those are the eight of them. So the big ones. And then each student on the group of five, would have different questions to answer. So they all would work on a project that you would need to answer. Why is it that you doing what you're doing? And I would need to say, well, what is the alternative to it, and so on. So that way, the entire curriculum for 1 year would look like this. This is the 1 year curriculum. We call it an academic sprint. So once again, this would be it's one of those sprints. The length of the sprint is 3.5 weeks. And after that, you have something you can call toolkit. I think I don't have it. Toolkit, which is that you may need a little bit more extra knowledge about partial differential equations, or I may need to learn a little bit more about optics and so on. But rather than having math, physics, chemistry concurrently, and what we would do is we would embed all those math, physics, chemistry concepts in finding a solution to a particular problem. Now, so you will see that there will be also for about 2 months or so, community-based project. It's very important to make certain that you are going to be embedded in the community, so people understand why we have students. I'm sure in your area you have those projects with community, no doubt. But in general, our undergraduate students, they don't have it, or not at the level that perhaps we should. So you will see there will be 15 of those academic sprints. So there is another controversy potential. It means that you would stay at the university for 46 weeks out of 52. Now, during those sprints, of course, you would spend some time on the premises of the company. So it would be like a perpetual co-op, so to speak, and the company would pay you for what you were doing for them. So there will be an income. Now, it means also that it would accelerate your degrees. So in principle, in engineering, you would be able to get masters in 3 years and 2 months. Now, so what that means, of course, from the student perspective, you would pay less for your education. Typically in engineering, it is 4.5 years. So you pay less. You would enter the workforce much earlier. And what we would do is it would also give you an opportunity over the period of time to work with many, at least 25, 30 or so different companies. So if you wanted to, if you liked something, it would be much easier to get an employment, and vice versa. It would be easier for the companies to test drive the students as well. Now, what we initially we are proposing is that the group of 5, when they start working on those projects, they would go throughout the entire time, rather than changing. What it means is that, and why so it was suggested by some of our employers, because they said, well, rather than hiring one person, we would be interested in hiring a cluster of 5. Because they already work together, they on a variety of projects, they know how to, what's the dynamics between them. So it's an opportunity. So if this is the pathway for one student. And what we really wanted to do is to, if we expand it, let's say that we would have ultimately 1,000 students, the academic program would look like that. It's a mosaic. So you would take this part, this. I would take the other one. Professor Plummer, he likes to study harder, so he would take substantially more, and so on. But essentially, it would make it very individual. It would make a nightmare to the administrative team to look after it, but it would be seamless from the student's perspective. And at the end, I said that we're here because of you, and we are for you. So that would be the what we call it at the moment liberal engineering. Now, liberal means that we are trying to liberate engineering from itself. I doubt that we're going to keep that name, well, especially in our province these days. And it is related to some political parties, so we want to make certain that it's not being seen that way. But nevertheless, look. And I can appreciate this is very weird, off the deep end of what is currently being done. And I'm pragmatic enough to understand that we may not be able to get it all there, the way that I'm presenting. But you don't want to limit yourself from the outset. You see, you go off the deep end if necessary, and in order to bounce your ideas out, to listen to other people, and to find a healthy consensus. So yes, the student at the end, because you will be also assessed, the student would develop a fingerprint. That will be, this is who you are, what you do, how you learn. And what we really wanted to do is to place, in this program, the overarching purpose was to place employability of our students at the core of everything that they will be learning. And by the way, there is a big difference between employability and just getting a job. Getting a job, we would then create, I don't know, mechanical engineering, civil engineering, and then you are a mechanical engineer, this is your job, and so on. We want to make certain that you will be prepared, our students, everyone, will be prepared for a variety of employments, a variety of jobs. And that's the way we believe at the moment that that's the way to do it. Now, let me leave you with a 5-minute slide. And I will be interested actually in your comments on that as well. Some time ago, we had a debate on, it was an Oxford-style debate on a subject. We said we had a motion, and the motion was that this House believes that technology is making us more human. That is controversial. But if you want to have a nice panel discussion, that's what you want to do. So on that panel, we had a few interesting individuals. We had Garry Kasparov. Garry Kasparov is one of the best chess masters that ever lived. It's an interesting fellow because he was the only chess player at that time that played against a machine. The machine was IBM Deep Blue. He won once and he lost once, so he can say something about it. We had a woman from Barcelona. She is a cyborg, so that she doesn't use a name. She's a cyborg. She's got some sensors in her body, and she monitors everything. We had a prof, a young professor from Harvard that deals with issues related to sustainability. And we had a very controversial writer from an Irish writer. So it was very interesting. What we did is we took the the Oxford debate is such that you put a motion up and you take a vote prior to the debate. And then you take another vote after the debate, and the team that will be able to change most minds wins. So you may have overall less vote, but you changed the most minds and you won. That it was very interesting. So I'm going to leave this with you, and perhaps we could open it up now for a conversation. To be honest, I don't know how much time we have, except that Professor Plowman told me that the other speaker we were planning, we're not going to have. So I took substantially more time than I perhaps normally would have.
And we certainly appreciate it, and we certainly have time for some conversation.
We do?
We do, yes. Absolutely. So why don't we open it up?
Yes, let's open it up. And look, don't be afraid whatsoever. I'm very down to earth individual. And by the way, I like critique and different opinions. By the way, I love different opinions than mine. I'm not interested in my own ideas. I know them quite well, too perhaps. I'm interested in what you think about it. Who wants to go first?
I'll ask. Just about the supercritical water. I thought that was really interesting when you talked about that. Is there any recent developments in that in terms of like creating like a way to on demand have hydrogen energy?
What a brilliant question it is. And I left a few things about supercritical water to get that question. Because you see, you may think there's a person that we invited, he speaks so highly about supercritical water, great results and so on. Why is it that we are not using it? Because the truth is, there are no commercial units that use supercritical water for to generate hydrogen. Now, the main problem with supercritical water is that it is one of the most corrosive media that you can find. So, if this was a stainless steel reactor, it would perhaps survive for less than a month, and then it would be eaten up because it's so corrosive. And you notice that what we were using, it was a diamond. And in reality, you're not going to use diamonds in industry to do it. You could we used also platinum. Pure, it was beautifully, horrendously expensive, of course. So the problem with supercritical water, or the problem that is not being currently used on a commercial scale, is not with the medium itself, not with the idea. It's about finding a proper material that it will be able to handle such a corrosive environment. There are some materials, and those are being used by NASA and so on, very expensive at the moment. Once we will be able to find proper material, then it's very likely that the technology will find its application.
Cool.
Great question. Yes?
Just wondering, like, also, if you found a material, like, that would work, would it not be still pretty dangerous? Because I'm just thinking of, like, such a little thing that's like 2 hockey pucks and 1 screw was missing and it went through so many walls. Like, could that not be pretty dangerous?
Well, it would be only dangerous if you are, if the purpose is to generate hydrogen. So indeed, you have to be careful. But one of the applications currently of this technology is to deal with medical residues. So that you don't generate hydrogen, you don't generate oxygen separately. You are able to take highly cancerogenic the substances, that the residues from operations and so on, and you can dissolve it to individual atoms. Currently, most of it is being incinerated. Now, if you burn a material like that, then the polycyclic aromatic hydrocarbons would be generated. Now, I have to say that the largest reactor that we were able to use, it was built in Orléans, in France, just around 1 hour south from Paris, to deal with residues from wineries and forestry. The beauty of the supercritical water approach is that it doesn't really matter what is the moisture content of your feed material. And agricultural residues, they contain a lot of water. So typically, the biomass, how do you generate energy from biomass? You have to dry it out to eliminate water, and then you ignite, and then you burn, and you generate energy from it. In supercritical water, the more moisture you have in your feedstock, the better it is, because it's a source of that as well. So the biggest one, when we built it, it was able to handle around 200 kilograms of biomass per hour. So it was maybe half of that space here of the seminar room. And it was not for the purpose of generating hydrogen. It was rather to just generate synthetic gas. So synthetic gas is a combination of hydrogen and CO2. Hydrogen and CO. Very high heating value or very high energy value, but safe from that perspective.
Yeah, you also said that so one of the other products besides hydrogen is CO2,
Yes.
and that you want to minimize that. Is it pretty easy to minimize that?
Yes, by the way, most of the pollutants that we know, so what do we know? We know soot or solid particulates, nitrogen oxides, sulfur oxides. What else is regulated here in Canada? Well, certainly the polycyclic aromatic furans, dioxins, you can easily not even generate. So if you have them in the feedstock, then it's very easy to decompose, destroy. Essentially, the products are only 3, maybe 4. So it's hydrogen, CO, CO2, and oxygen, any combination of these. So the example that I gave you, it was to mix hydrogen with CO, which is safe, and it is highly energetic, avoiding CO2 and O2, or minimizing it.
My question's on the idea of no lectures in the future classroom. I'm sold. You've sold me. I mean,
No, you're not the only one. When I go to high school, I tell you, those kids are very much interested in it.
well, my question is regarding the controversy. I don't think it's very controversial to take an idea. But here's something we've been doing for hundreds, if not thousands of years. Maybe we've learned a thing or two and can improve on it. I buy into that. What I'm wondering is, from the controversial aspect of it, what other pushback is there for maintaining lectures as they are? Why keep them?
Look, so the educational system is designed at the moment around professors rather than students. And well, why so? If you look to your professors, then they will tell you that most of the universities require a 40-40-20 distribution. 40% of professors' time would go to teaching and education and so on. Another 40% would be research, and the final 20% would be to contribute to what I call it citizenship, or although administration. It's not just administration per se, it's truly citizenship. So the process of employment of a professor, process of progression, tenure, and so on, it's all designed around that. So what we would need to do is we would need to change the way how we think about education. Okay, so I'm going to say something, and I know I'm going to put myself in trouble. Because one of the facets of the higher education system that we have is also tenure. So at some point you get tenure, and then it's a lifetime employment, which is terrific, and it's to protect the academic freedom and so on. I think what we should do is we should find a different way to protect academic freedom, not necessarily through that pathway. By the way, it is highly, highly controversial, so it's not neither my role to deal with it. It depends on the university. But what I think is that the way how we would be able to implement some elements of what I was saying is if we truly, truly are going to put the student at the core of everything what we do at the university. And by the way, I don't believe actually that what we are proposing is the only good solution. I think that the best solution in education is to have a variety of options. And when I was a dean at La Salle School, I had some students, they came to me and said, look, we don't want to work in groups. We rather try working alone, or from time to time we would consult with the others. So we need to find, we need to develop an educational system that allows a variety of ways to approach students, and a variety of ways for you to learn. One of the ways is what I described, and I think that it works all right for the academic, for engineering. I don't know if it's going to work that well for in social sciences or humanities or in business and so on. So I think that the main pushback or obstacle is just ourselves, profs. We are too conservative, and once we get into the comfort zone, then we like to stay there. I'll give you an example. So when we created that school at your La Salle School of Engineering, we got quite a lot of funding to build a building, completely new facility. And of course, the university wanted to build a box because it's inexpensive. Just build a box. So we went out, we brought quite a lot of independent funding, and we insisted on having a different facility. So it's, when you look at it, it's called now Bergeron Center for Engineering Excellence. Doug Bergeron gave us 10 million towards it. It reminds us a cloud, because what we wanted to do is build something that represents engineering. And it is not true that engineering is about precision and measurement and so on. Engineering, like many other fields, is about ambiguity. You really don't know what it is. So, the cloud is a very good example of ambiguity. I don't know if we have, do we have a connection here with, let's see if we have it, internet connection. Actually, we do. So I'm going to show it to you because it will be easier on center. Center for Engineering Excellence. Let's see if this is what it's going to give us. No, so you'll see. Okay. So that's how it looks like, actually. So this is what we built. Those are not images. So this is how it really looks like. So, just to tell you, so we built something completely different. From afar, actually, it looks like a, especially in the evening, when the lights are shut there, it looks like floating cloud. So what we did, it is, those are windows there. There are 200 windows around, and no window is the same as the other, and no window has the straight angle, and we did it the way that whenever we have sunshine, that it reflects the way that it creates so much natural light inside. And then it was a controversy, because of course, you see, professors wanted to have offices on the periphery. Then you see a beautiful view and so on. And then laboratories and social spaces for students would be right in the middle, deprived of natural light. So I didn't exercise my dean's powers too often, but it was fundamental. So what we did is we created social spaces, beautiful social spaces, laboratories, these kinds of classrooms and so on the periphery. And we placed professorial offices right in the middle. And it was on purpose. You see, because typically when you want to go and see professor, you would go to professorial office, and then professors feel in their comfort zone in their own surroundings. That's the worst thing, because then you're not going to get that much out of the conversation. You would get much more if you interact with professors outside of their comfort zone. So what we did is we sort of naturally forced professors to interact with students in those social spaces. So it's after a while, indeed, a lot of interactions. It was in the social spaces. Now, I have to say that what we did, I don't think that we have a photo here, in that building, everywhere, all walls were writable. So in laboratories, in classrooms, on the hallway, even in the elevator, you could, if you had an idea, you could write. So you could always find a really cool place to be there, stand up together with the professor, and then interact. Now, it is true that on 2 occasions there were some one drawing and one sign that was not necessarily appropriate. But look, those are the risks. What we did as well. There's another thing that so by the way, what we had done is we were able to find a way to show that students are at the core rather than not. Now, the other thing that we created, it was space that belonged exclusively to students. So we called it the anarchist lab. Right? It was a space that no professors or staff were allowed to go, except if you invited us to do so. And we provided tools for students and 3D printers and some other things. So it was they were able to relax, but they were able to do something useful at the same time as well. Again, it was fundamental to do so, because then you're showing that you're trusting your own students. And in academia, we work based on trust. So that's a fundamental approach, and you have to do so. And I didn't believe it. You see, students regulated themselves more stringent than we would develop something for them. So yes, there were governments and committees. And at the end, I asked them to eliminate those committees. The worst thing is to have a committee. You know that the camel is the horse designed by the committee. And that's That's sometimes how it is. It's not easy to have change. By the way, change is in academia. A lot of people will tell you that a little change is good, no change is better. Right? When I attended some meetings with colleagues from business, they would tell me that the only person that really likes change is a baby with a wet nappy. Right? People don't like change that much. So you see, if I were to give an advice, especially to you, please don't be afraid whatsoever to do things in a different way that your instinct is telling you. Because we work and we think in a schematic way. So try to push it in slightly differently. Because the truth is, there is plenty in store for those who are prepared to follow a bit of a different drum. Right? No, don't be afraid to do it, and especially if you're so young, you have an entire life in front of you. Anyway, any other comments?
So coming from the not so young.
By the way, no. You're wrong about it, because we are young up here, down there, and in our hearts. I consider myself truly a youngster, although I'm almost 60 years old. So, but you feel, I feel much better now than when I was 22. Yes, so we are all young. Got it.
I think from observing for so long, and if I understand you correctly, one of the things that changing the education system would do would be to have people think much more critically.
Yes.
And then when you go out into society and when you start to discuss problems that we're having, what you get is what they've been fed, and they don't critically think, so that they become very averse to change. So coming through this type of education system where you're always changing, it's part of it, it's built in, and always critically thinking, then you have a much more productive citizen.
That is true. So, and indeed, I have to say that the current educational system, from that perspective, is delivering something that is quite all right. Because you know how to think critically, you know how to analyze things, how to synthesize things. What's really important, especially in my own field, in engineering, what we need to do is we need to think about everything else from the perspective of a human being. So we have to put a person in the middle. So we would design a bridge. It would be terrific if we designed a bridge that is beautiful. It's absolutely. But we have to find out what is the main purpose of it. How people with different abilities or disabilities will be able to utilize it. One of the ideas that we have for Brock's engineering is to create something, we call it tentatively, Invictus engineering, which is the engineering program that is designed for the people that were injured, such as service women, servicemen, veterans as well. There's none available at the moment. So again, putting a human being at the core, and then developing for different fields, different approaches, would be ideal. I have this. Whatever I do, I have different principles. So one that I wanted to share with you, I call it CSS. It means it is class, substance, and style. So whatever we do in academia, especially as administrators, professors, we should be doing substantive things but we should be doing it with class and in style. I tell you, so one example would be this Lasson school that we created, a Renaissance engineering. And what we wanted to do is to make certain that this new school, new academic program, will be approved by Senate at York University in as unanimous way as possible. So I went around the university, met with a lot of faculty councils, and I wanted them to hear from me directly what we want to create, because if you tell somebody, then after a chain of comments, it's a completely distorted message. And it was one of very, so when the vote was there, it was one of very few votes that it was unanimous. And getting anything unanimous through any academic senate is difficult. York Senate is specific in that regard. So that was leading the CSS principle, because we did create something truly substantive, and we've done it in a way that it resonated with the others.
Just thinking about the pathway that you showed of like one single student through the program, I'm just wondering about the logistics of having, you set up to potentially 20 partnerships through a program. I mean, I've never personally had to develop partnerships with different agencies, companies in the community, but how realistic is it to form that many partnerships in a community as small as the campus area?
I can see that you're very pragmatic about it.
Yeah.
If I were a student, I wouldn't care whatsoever about it, because that's the role of people like me or other professors, including Professor Brown. Our role is to go out and bring partners to the university, employers to the university, in order to provide the academic projects. Now, so I wouldn't worry. I wouldn't worry about it, because if we were to implement this program, we would have solved that problem already. But you pointed out to something that is absolutely fundamental to the success, potential success of this approach, and it is to have partners. Partnership is fundamental here. And that's why I'm saying that it's not just industry, because what we want to do is to create partnerships with community centers, with financial institutions, with a variety of industries, predominantly manufacturing and agricultural industry. And indeed, I agree with you, it would be very difficult if we relied exclusively on the partners in our region. Niagara region is relatively small. We have, the population is, I think, 500,000 altogether. So that's why we have to go out, including bring partners from outside Canada. I didn't mention this yet, but one of the potential requirements of this program would be for the student to spend at least one, preferably 2 of those sprints abroad. And it is, well, I'd say 2 sprints, because 1 sprint would be an academic work, but the other 3 weeks, what I'd like to see is for students to have an opportunity to learn more about the country that they know. Let's say if you went to Italy, to learn more about history, about customs, about architecture, about geography, about people, because that is as important educational element as it is to learn how to use thermocouples to measure temperature. Yeah, so that in order for us to be successful, it would need to be expanded. Now, so the other, I mentioned partnerships. The other element of success would be to create meaningful partnerships with other academic institutions. It would make sense for us to engage with our neighbors and friends from McMaster, from Waterloo. These are good, traditional, but good engineering very good engineering programs. So we would benefit from it, no doubt. They would be able to benefit from testing out a new type of pedagogy. I think it would be good for us to create a partnership with the college, Niagara College, because if we're saying that we're going to place a student at the core, it would be great if we created a program that, let's say, students from the college, after 2 years or so, they should have an opportunity to seamlessly transfer to the university program. Difference, by the way, is that if you complete education at the college level, you are not eligible to become a professional engineer because the programs in the college are not accredited. At the university, it is accredited. So we would create an opportunity, a pathway, for those who are interested in doing so, and vice versa. It's likely that we're going to have some students that may struggle at the university setting. So rather than dropping, they could transfer to the college and complete the technology the degree. So again, that way, we're creating more opportunities for young people. Yes?
I think you've kind of touched on this a little bit throughout your discussion, but what would the expectation for the specific engineering students to collaborate within other disciplines? Would they be collaborating with sustainability students at all?
Well, right. So as I mentioned, you see, the only way to make it successful, we would need to build this new program on a very strong foundation of sustainability. Because we are asking those 4 questions. There will be more questions, but 4 fundamental questions that are surrounded by the sphere of sustainability. Sustainability is the critical element of our lives. So that's why what we would need to do is, how I would see it, is that the sustainability component would be a critical and important element of the program. It would need to be there. I don't know how we would be, how we were going to do it, but at this stage. But I think that it would be better for us to listen to young people like you. You may have better ideas than we do how you would like to see yourself in such a setting. But indeed, sustainability and the center would need to be there. I have to say that I don't worry whatsoever about the role of the center in this project and other projects, because the truth is that the Sustainability Center is one of the very top strategic priorities for the university. It means that the university, I believe, is prepared or will be prepared to invest heavily in the activities of the center, to expand its boundaries, and investing means that there will be more people that would be hired, there will be more people that will be visiting, there will be more students, and hopefully will be more scholarships and for you to attend, because we have to create incentives. And certainly, if we were to develop this engineering program, the environmental engineering, environmental sustainability, especially in the environmental engineering, would be fundamental. Yes.
My question relates to, I think, more along the lines of biomass work that you do, and apologize. It is related to cannabis, and it only has to do with the fact that this is the day that you're here. And a really good friend, lifelong friend of mine, who is an engineer, chemical engineer. He is the CEO, so chief operating officer of a large cannabis operation here in Niagara. My understanding is there seems to be a innovation gap here currently, and I think it's related to the scramble just to be compliant over to be innovative right now. So once you harvest the buds from the cannabis plant, Health Canada's guidelines, you have to render it. You can't propagate from it. So my understanding is right now a lot of these companies that are sending in his particular case, it's going to landfill. So they're low volume right now. So the plants are being combined to neutralize. I won't say how. It's pretty embarrassing. I see a lost opportunity, and maybe it's just because the focus is being compliant over being innovative, but I would be interested on your thoughts, and it seems like there's a potential research gap there that could be very interesting.
So, by the way, how I, as a researcher, how I look at cannabis, marijuana, and so on, to me, it's just another source of energy. Utilizing it in a slightly different way, so not necessarily, because if you smoke it, it's also a source of energy. But for me, what I look at it is that it is the just chemical with wonderful composition, and we did work with marijuana as the potential feedstock for this supercritical water. I can tell you, it is much easier to deal with marijuana because of the type of the chemical composition that it is. So it's very easy in supercritical water. What you do in order to decompose it, you have to break bonds between different chemicals, and it's much easier to do it for this particular the feedstock than it is for the others. So I think that there's a tremendous opportunity in our country to open up significant and substantive research about marijuana. And it's not only research related how it affects human beings when you use it, but it is from the chemical perspective, how we would be able to utilize this crop, actually, how we would be able to utilize it for a variety of purposes. And it could be for medical purposes, and it could be for human individual use. But I look at it from the energy perspective, and it would be a terrific medium. The only way that I think we should approach it is not separately. So the worst would be if there would be certain research under the umbrella of NSERC. NSERC is the grant agency, federal government granting agency focused on sciences and engineering, and then CIHR, which is humanities, and then, it's a medicine, and then SHERC, which is, the best would be to see if we would be able to create a platform that researchers from different fields that would be able to approach the problem in a more comprehensive way. I'd be happy to, I'm a chemical engineer as well, be happy to meet up with
I haven't talked to him for a while because he's always away, and I caught him this morning, and I just said, hey, what are you doing with your weights? He goes, I'm not talking to you, I'm not telling you. So I'm like, oh, come on. Yeah, and he also offered that if you ever need a class tour of the operations, if that's not, stop changing the subject.
Well, a lot of people would subscribe to that. Yes, go. Please go ahead.
Janusz, we had a question from, this is live streaming, so from online. Someone asking, how is data science changing how engineering is taught in relation to sustainability?
Yes. So actually, the concept of data science, or essentially dealing with a flow of data, especially with regards to what we discussed, and I'm talking about energy and environment, not an education component. It's becoming really, really important, and I tell you why. Because there's a lot of data that is being generated that is not necessarily verified. And it's difficult to deal with it. The data that is typically published in journals, that's all right because it went through a peer review process. But a lot of laboratories, quite a few researchers, what they do is whenever you have some set of data, you're going to put it out online in order to, in the future, to claim that you have the priority with regards to a particular concept. So I think the important thing would be for us to develop a methodology that we would be able to distinguish between data that you can trust and data that would need to be verified. I'm not saying that there will be data that we are not going to trust that would be inappropriate, because you have to assume that all the data would generated in a good faith. The only thing is that you have to have a mechanism to verify. So trust with verification would be a good approach. There are a few companies that are working in this area. So, for example, Cisco is one of the companies, and they are pushing the Internet of Things concept. And it's likely that we may create a partnership with this particular company. It would be great to bring Cisco more to Brock. They are already present, but we would need to expand it.
Maybe one last question just before we wrap things up as we head for the hour.
Okay, you have a question?
Yeah, I had a question kind of related to waste biomass, say from cannabis or viticulture, agriculture in the region. And how do you see the kind of, the future for microbes degrading these wastes to produce energy in the form of, say, methane or hydrogen? Right. And is that, as opposed to supercritical water? And in terms of symbiosis,
yes.
Do you see that as a good avenue?
Indeed, I do. To tell you what, you see, like in life, it's very good to have as diversified portfolio as reasonable. So the portfolio of friends or financial investments. So the same thing is with energy. I believe strongly that there is a role for many different forms of energy, including generating energy from fossil fuels. It would be inappropriate for us to insist that what we should do is we should not be using fossil fuels, because it would be prohibitively expensive for countries that are less fortunate than we are, for example. So I think there is a role for renewables. I think there is a role for the biological type of processing that you described. For example, it could be with using a variety of living organisms that would digest and then generate, say, could be hydrogen, actually.
Yeah.
The only thing is that what we need to do is we need to be realistic about it. What is it that may be the prevailing pathway? Because in order to conduct the type of energy generation that you described, we would need to use substantial volumes in order to generate a meaningful amount of energy. It also depends on what is the purpose, because if we were to generate, say, ultimately electricity, and it may be very difficult because there are certain grids of energy that are established, so we would need to link up with it. It's much easier to do so using the biomass when you simply a launch field, and then you wait and generate mostly CH4, the natural gas, or methane. When you typically what is being done currently with biomass is not what I described, but rather combustion. So it's those residues are being burned. So there is a role also for nuclear, I believe, because if you look at France generates 85% of electricity by nuclear reactors. It's a completely different approach than what we have, for example. Because in France they have a lot of very small nuclear reactors. So if you have a problem, you typically would have a small problem. Unlike, if you remember Chernobyl, I don't know if you remember, it was a huge reactor. And if there is a problem, then it always will be a huge problem. So safety would be the fundamental. There is, of course, a role for biofuels. What you described is sort of bioenergy, and I think that bioenergy, biofuels, their contribution to the overall energy balance will be increasing steadily. Perhaps some biological solutions as well. Great question. All right.
So much for coming today, Mr. Tokens of Appreciation.
Oh,
And
is it made from sustainable process?
I absolutely think so. It's certainly given us so much to think about today. Everything from alternate ways to produce energy, truly multidisciplinary in our thought process, and looking at other ways to approach education and teamwork. And I think it's very appropriate, and it's given us a lot to discuss. So thank you so much.
Thank you again. By the way, it was my first seminar that I'm giving at Brock, so it's, from my perspective, it's part of history. I'll always remember. And if you wanted to have a conversation with me and you wanted to follow up on anything, not only those things that we discussed here, please send me a line, and I will definitely be happy to share a conversation with you. And I think you have, well, you have my email. Please come and see me. All right? Thanks so much. Sometime.
If you're around, or it's not a problem. You are around? Okay.
Together. Okay. Absolutely.